So four identical rods are hinged at their ends to make a parallelogram ABCD. The hinge joint A is rigidly attached to a wall and the opposite joint C is pulled away from the wall. The constant acceleration. Find acceleration vector of joint B. So first we'll see a famous wrong method, that is this be A, this be C, this be the AX component of B, AY component of B. So in the geometry of the problem, we can come to the conclusion that this will be theta, this will also be theta, this will be 90 minus theta, this will also be 90 minus theta. BC, velocity vector of B along BC is equal to velocity vector of C along BC. Acceleration vector of B along BC is equal to acceleration vector of C along BC, and similarly for AB. But this is wrong because see, if this is the velocity vector in any direction, if you assume this to be the velocity vector and this to be on this be some point A, let's say this be some point O1, this be some point O2, let this one have, let's say that the direction of this one be n cap, the perpendicular component that be some t cap, sorry, or we'll take this one to be t cap and this one to be some n cap. This O1, let it have Vx n cap plus Vy t cap, and this one be, let's say, some Ux n cap plus Uy t cap. So from the rigid body constraint, from rigid body constraint, the problem with this method is, before we see this, just a second. I forgot to tell what is the actual problem with this. So this will imply that from this geometry, 90 minus theta, A sin theta will come out to be Ax sin theta plus Ay cos theta, and this will tell that the acceleration, if you take along AB this direction, Ay cos theta is Ax sin theta, and if we solve these two, you will get Ax is A by 2 and you will get Ay is equal to A by 2 tan theta. Now this is wrong, and the reason why that is wrong is, as we saw, for rigid body constraint, Uy t cap is equal to Vy t cap. Now if you differentiate this, Uy t cap, derivative of t cap with dt time plus derivative of the speed by dt along t cap is equal to Vy derivative along t cap with time plus derivative of Vy by dt along t cap. But the method shown above, we directly used only these two components on t cap and haven't included the derivative of t cap with time, those things in our equations. So whenever something goes bad, the number one rule, whenever stuff gets complex, number one rule will be to start from distance generally and then differentiate it for velocity, and we'll go with the same thing, except if it's relative concept. If it's a relative concept, then we'll have some slight changes. So we'll apply that. We'll assume, since they were initially, these 2 points were initially together, this will be at some point at square by 2 comma 0 0 comma 0 x comma y. Clearly from symmetry, because this angle theta isosceles, x is equal to at square by 2. This is very much simple, I guess. So x is equal to at square by 4. So acceleration along x direction will be a by 2. I think that's far enough. So by assuming this to be, then so we have this one moving with speed v is equal to at, and let this move with vx and vy. Now we can apply the rigid body constraints. The main problem, and also another problem that we had in this method, was we applied the rigid body constraint, but the same thing was we did not include these components. That was the problem over that, but here we'll take care of those things. So 90 minus theta also, Vx will come out to be 80 by 2. If we look at this rod, BC, Vx cos of 90 minus theta sin theta is Vy cos theta in this direction, and in this direction it had Vx cos 90 minus theta sin theta is Vy minus Vy cos theta. And this one was moving with 90 minus theta, V sin theta, sorry, this is V, this will be V sin theta, sorry, this is 80 sin theta. So I can come to the conclusion, Vx sin theta plus Vy cos theta equal to 80 sin theta, and we proved our work from the similarity. Vy is equal to 80 by 2 tan theta. From here I can tell Ay is A by 2 tan theta is 80 by 2 secant square theta d by dt. So then after this, what is dt, and now we have applied the first constraint. Let's call this part of the problem as BC constraint. I would like to highlight this point. Now if we go to the AB part, AB constraint, Vy, Vx, so theta 90 minus theta, and also please make sure that you don't mess up this as by taking this as 90 minus theta, you don't default take this as theta. We've done it a lot of times. I did that when I solved this problem. So Va cos theta plus Vx sin theta in this direction. We'll have Vx sin theta minus Vy cos theta. Since this point is at 0, 0 rest, so you can tell Vx sin theta is equal to Vy cos theta, which implies V by Vx tan theta. Yeah, did we get this relation earlier? Yes, we did. We also got it earlier itself. So now how do we solve for this d theta by dt? That's the one making the problem. We can tell one more thing is that here we'll get the third constraint. So third constraint, look at AB. This length that is given, let's assume this is D. One thing we can clearly see is that D is constant. Since it's a rod, this is y, this is x square plus y square is equal to constant. 2Vx, differentiating with time, if you differentiate with respect to time, 2Vx x is to Vy to y is 0. Vx into x is equal to minus Vy into y. Now if you again differentiate this with respect to time, Vx square plus Vx into Ax is equal to minus Vy square minus Vy into Ay. From here, if we substitute some of those values which we got earlier, got Vx is 80 by 2 whole square plus 80 by 2 into A by 2 minus of 80 by 2 tan theta squared, because Vx, yes, that's right, minus 80 by 2 Ay. This is the important constraint. You could have told that since d is constant, the locus will be that of a circle. From there you can tell omega r, you can derive like that way also, but I done like this. So 80 square by 4 this into 1 plus tan square theta is 80 by 2 into A by 2. Let's put this to minus 80 by 2 along Ay square into, sorry, ay will become minus ay is equal to at by 2 1 plus tan square theta plus a by 2. Yeah, so wait, yeah, sorry, I made a mistake here. I'm differentiating. This is supposed to be the correct equation. This one is dimensionally wrong, it is realized. Delete. So 8a by 2 whole square plus x component comes out to be what? Yeah, we don't have, yeah, x component is 80 square by 4 and 80 square by 4, and this one is a by 2 is equal to minus of 80 by 2 whole square tan square theta minus what is the y component, y coordinate. Do we have that? We don't. Yeah, but we have, but from this triangle I can tell that theta y x y is equal to x cot theta. So I'll substitute this minus x cot theta ay, and x is 80 by 2, sorry, 8t square by 2, 8t square by 2. Wait, oh sorry, x is 80 square by 4. This would imply 8t square a square t square by 4 secant square theta plus a square t square by 8 is equal to minus 8t square by 4 cot theta a by, and yeah, after this what do I do? This can be written as a by ay cot theta into minus 1 can be written as a secant square theta plus a by 2 minus ay cot theta can be written as a into 3 by 2 plus tan square theta, and there I can tell a is equal to minus a into 3 tan theta by 2 plus tan cube theta. That's it. Yeah, so this is how you can find ay component also, and this is the answer. And let me just verify once. Yeah, and that seems to be the answer. No, there seems to be a slight mismatch. No, I think this is the correct answer. If you look at point D, it might be the other way around, but no, this is the correct answer.